Hello there, this is exercise 17C. We're saying obviously in two parts, 17C.1. We today, as our first part and first look at this, we're going to try and understand what a binomial distribution is and when we can use it, when it's useful, when we can't use it. And it all comes about when we're trying to do some kind of experiment, an event, might be rolling a die for instance, and we do it for a set number of times. And we're trying to see how many times a certain event comes up. So it might be, for instance, I roll a die, and I'm interested in how many, I don't know, how many fives I get. So I'm looking to see how many times 5 comes up. And obviously, I expect there to be, I don't know, a probability of getting 5 of a sixth. And what's interesting about this outcome here, 5. Now, if I'm interested in getting a 5, the only other thing that can happen is I don't get a 5. It's not a 5. Even though there's lots of different outcomes, obviously there's 1, 2, 3, 4, and 6 would be the other outcomes. As far as I'm concerned, doing the binomial distribution is all about things happening or not happening. That's what the binomial distribution does. It comes about from this word meaning bi, obviously. Take for instance an example would be a bike. A bicycle has 2 wheels, and this has 2 possible outcomes, and that's what we're looking at here today. So some events only have 2 possible outcomes. I either get heads or tails on a coin, for instance. There's a 50p piece. I can either get a tail or I get a head. I'd be very surprised if it landed on its edge, for instance. When I have 2 people running a race, either A wins or B wins, assuming, of course, they don't draw. Again, you can presumably get reasons why these things aren't really binomial. But as long as we assume that one person wins a race, either A wins or B wins. We either get heads or tails. There's 2 possible outcomes. And of course, what I want you to note about this is that these 2 events don't have to be equally likely. And so heads and tails, you kind of assume probably they are, but they don't have to be. It might be one of those dodgy coins that people always say they've got. Heads and tails you would assume would be equally likely with a probability of a half for each. But these 2 guys running a race, he could be Usain Bolt for all I know against me, and I'm not going to beat Usain Bolt. So therefore these don't have to be equally likely. It could be, but this one, A winning might be 0.9 chance, but B winning might be only 0.1 chance. But they're still binomial. He could win. He could win. But not necessarily equally likely. So just bearing that in mind, some events appear to have lots of outcomes. This is kind of like the one I did right at the start, but that we only interested in 2 of them. So tomorrow's weather, for instance, might be sunny, or it might not be sunny. Now there's 100 different weather systems that could strike tomorrow, but if I'm only interested in sunny or not sunny, there's only 2. Right here now, I'm sitting here and the rain's falling on the window. Doesn't matter. All I care about is either sunny or not sunny. When I roll the die, it could either be a 4 or not a 4. Well, there's, as I said, there's 1, 2, 3, 4, 5, 6. Could happen, but I don't care. I want a 4 or it's not a 4. So these kind of situations where we effectively end up with 2 possible outcomes, whether it's because there are 2 possible outcomes or we pretend there's 2 possible outcomes, these can be modelled by the binomial distribution. There are certain rules when we can use the binomial distribution and when we can't. So just bear these in mind. There's got to be 2 possible outcomes. I've hinted at that already. But as you've already seen, we can make it appear to have 2 possible outcomes. We're going to do whatever this is, and we're going to repeat it n times. And that's because we are, in essence, with the binomial distribution, it's all about doing the same thing lots and lots and lots of times. But notice the 2 assumptions. These are generally called the assumptions. We have to assume that every time we do the experiment, tossing a coin, rolling a die, even 2 people running a race, we have to assume that the probability of one person winning is the same every time. And by definition, that person not winning is the same every time. And we have to assume also that the trials are independent. That means what happened before doesn't affect what happens in the future. These 2 assumptions are important. Constant probability and independent events then are known as the assumptions that we need to make in order for a distribution to be considered to be normal. Now you often get asked what assumptions have you made in answering this question, and that's the kind of thing you'd write. You'd write Well, I've assumed that I have constant probability of whatever is happening, and that the events are independent. That's what I'm meant to write. So we look out for that later on. Now, when we have a binomial distribution, then this is the way we write it. We write x is distributed. This little squiggle is distributed. It's not some random squiggle. It's meant to be that shape. Distributed binomially. The B stands for binomial. Now the n might be, for instance, I've done this experiment 20 times. The p is the probability of success. So it might be, for instance, my chance of beating that Usain Bolt fellow in a race. My chance of winning might only be 0.1, and that probably is only when I trip him up before he even starts. Look, so here are 3 examples of for us to see if we understand these ideas of when it is okay to use the binomial distribution, when it is not okay. So let's have a look at the 3 examples. It says write down the distribution and say whether or not it is binomial. Okay, so it doesn't actually want me to work out the probability. And each of these says find the probability, find the probability, find the probability. But actually I don't want that. It actually says write the distribution down and say whether or not it is binomial. So I spin a spinner 12 times, presumably this spinner, and I want the probability it lands on a 3. And the fact it's 5 times, I don't care about this. I care about the fact that it's 3 that it's got to land on. So if you look at that there, what's the probability it lands on a 3? And that's obviously a quarter. There's 4 sections. So the probability it lands on one of them is a quarter. So the way I write this is x is binomial. How many times am I doing it? Well, it tells me that as well. It tells me I'm doing it 12 times. So n, p, we always write that order. It's always written in the order binomial n, p. So here it's 12, and what did I say? It was a quarter for the probability. So 12, a quarter. That is the distribution. And does it fit my 2 rules? I've got to have constant probability. Well, yeah, I'm spinning a spinner. I don't see why it changes every time I spin it. And they've got to be independent events. The fact I get a 4 now doesn't mean I'm any less likely to get a 4 next time or this time. Yeah, so I think this one is right. This is okay. Let's look at the next example. It says 2 dice are rolled until it shows I get a double. Presumably double 1, double 2, double 3. Doesn't matter which double it is. Find the probability of getting my first double after 10 throws. Oh, right. Now this isn't binomial. It might on the face of it appear to be binomial, and it's very nearly binomial. The thing I don't like about it is it's all about getting my first double. I'm not binomial. This would be binomial if it says find the probability of getting 4 doubles in the first 10 throws. You see, that's what I want from this. I want a set number of goes, and I want to be counting up how many times it happens. Here, if I was spinning this, I wanted to count up, and it said, what's the chance of me getting this 3 exactly 5 times? You see, I'm counting up how many times it happens. But this one, I'm not. I'm just waiting and waiting and waiting and waiting. And it says, what's the probability of getting my first double after 10 throws? This is not binomial. It's actual fact, it's a geometric distribution, which we do in further maths. But for most of you, you don't need to know that. Not binomial. And the reason is, there is not a set number of throws. Basically, we don't know what n is. It may appear that we do, but in actual fact, if I was doing it, my first double could occur on my first or my second or my third throw, and then I'd stop, because it says what's the probability to get my first double. So here, if I was doing it a set number of times, that would be binomial. The chance of a taxi arriving in the next 10 minutes is known to be 0.3. If I wait on 20 consecutive days, find the probability of getting a taxi exactly 6 times. Now this is nearly, I'm going to describe this as nearly binomial. The reason why I think it's nearly binomial is because on the face of it, it's this. It's x is binomial. I'm doing it 20 times, and I want to find the probability of getting a taxi, and it says the probability of getting a taxi is 0.3. Now, if that is an exact constant known probability, then this is right. It is binomial. I'm slightly dodgy about it, because just because the probability today is 0.3 doesn't mean it's going to be 0.3 tomorrow. There might be, no taxis about. It might be one of those days you sat there waiting for a taxi for hours. So my fear is on this. Let me just see what the answers are. Not binomial as probability not constant. Yes. So that is almost binomial as long as this statement here is true. The probability is 0.3, but my gut feeling is it's probably not true. A formula there. This is not a nice formula. X is binomial n comma p. So this is the posh formula. Now, usually it's written in the formula book like this. This is actually the symbol for NCR that we have on our calculator. So I'm going to have to show you that on your calculator. It's actually, you can see it on your calculator above the divide button. So if you press shift and divide, you can get that button up. An example of this then is if I have a binomial type situation with 10 trials where n is 10, the probability of success is 2 out of 5. And where I want to know the probability of being successful 7 times. So straight away I'm thinking this is X is binomial. It tells me it's binomial. I'm doing it 10 times. It tells me that here, and it tells me my chance of getting, being successful on this is 0.4. So this is what I want to type into my calculator. And my formula basically tells me, let's see if I've got this here. Yeah, so this is what I type into my calculator. This means NCR, as I said. I'm doing it 10 times, and I want to find out the probability of getting exactly 7 of these exactly right. So I press the 10C7 button, and then I have to do the probability 0.4 to the power of 7. Notice the 7 that's appearing. That's the 7 there. The probability of getting 7 successes is 10C7 times 0.4 to the 7. But then my formula then says 1 minus p to the n minus x. Notice 1 minus p, if p is 0.4, 1 minus 0.4 equals 0.6, and that's why this has appeared, 0.6. And notice that 7, if I'm doing it 10 times, I'm rolling this 10 times. If I'm successful 7 times, I'm unsuccessful 3 times. That's what that is meant to be. And notice it says up here, n minus x. 10 minus 7 equals 3. And if I type that into my calculator, apparently I get 0.0425. Try it, make sure you do. So again, I'll do another one using the formula. I roll a fair die 5 times. So already I'm thinking X is binomial. So doing it 5 times. Probability, what assumptions do you need to make about the event to model this by the binomial distribution? Well, for part A then I'm going to say constant probability. That's what we were talking about just now. And independent events. And when you're rolling dice, you probably can quite happily assume those 2 things to be true. What's the probability then of getting exactly 3 6s? Oh, I want 6s. Probability of getting a 6 is a 6th. So it says, what's the probability of getting exactly 3 of them out of the 5 of them? Notice that. Now my formula says I do 5C3. 5 because it's n is 5. 3 because I want 3 of them. And I then times it by the probability, which is a 6th, to the power of that 3. But then I have to times it by the 1 minus a 6th. And if you do 1 minus a 6th on your calculator, it will come up as 5 6. It's not really that surprising. 5 6. Now this has to be power 2, because this is the 5 take away the 3. And if I type this into my calculator, it's 5C3, 5 press first, then the C NCR button, then 3, times by 1/6 to the power of 3 times by 5/6 to the power of 2. And I reckon that is 0.032. That's what the answer is. 0.0322. Good. So it works. Now, we're out of time, and there's still loads to do on this PowerPoint. So I might do another one just to make sure we're okay. So all the best.